Okay, go ahead.
Today I'd like to tell you about the paper Weight Conditioning for Smooth Optimization of Neural Network. This paper includes both analytical resonance and numerical results, good results. So let's start with a general view and the main idea. The authors propose a method for normalization of weight matrices, specifically weight conditioning. And this in this paper, it's argued that by reducing the ratio between the largest and the smallest singular value of weight matrices, the landscape of loss function can be modified in such a way that gradients in different directions of the loss function with respect to trainable parameters become closer in magnitude. And this means that it's possible to make the convergence of the gradient descent method better in such a way, reducing this so-called condition number of weight matrices. Here you can see bar charts illustrating some experimental results. I will tell you more about numerical part of this paper in the end of the presentation, but here is some motivation. So there are three different architectures here. And for every architecture, there are three methods of weights matrix optimization. And the third bar in every chart is the usage of weight conditioning, explained, described in the paper. So this method demonstrates good results according to competitors.
So, Katya, can I ask a question? So, are they proposing to reduce this ratio in the initial conditions or during dynamics, learning dynamics, or both?
They perform some modification of real connections between layers. So they just multiply this W matrix on the left side, and then kappa changes. And as a result, they show it in their some theorem that landscape becomes better. Landscape
So,
of the loss
it's during learning. So it's not necessarily in the initial conditions, right? So during the learning dynamics. Okay.
Yes. During activation dynamic, I can show it now.
Oh,
So
okay.
you can see it here.
Okay.
And
But effectively,
this preconditioner depends on W.
I see. But effectively, this P times W is what the weight matrix is.
Yes,
And this
yes.
P is something that changes depending on W, right? So it's a function of W. So basically,
Yes,
you are
yes.
kind of restricting the space of W's where you are searching for. Okay, got it.
And now let's consider some notation. So for further analytical calculations, authors use feed-forward architecture for providing some proofs of theorems and etc. So let's consider it. F is a neural network which consists of L layers, and sub I is the number of layers in the ith layer. X is illustrates the input datas, and F sub k is the output at layer k. So phi is activation function, wk is a weight matrix connecting k minus 1 layer with k layer, and there is a linear activation in the output layer. So it's a standard. And a loss function can be arbitrary, but in the numerical experiments, they everywhere use mean square or binary cross entropy loss. And in the second section of this paper, authors consider some general calculations. So I think that this section is very important because it provides some fundamental results which can be used not only for usage of weight conditioning, but for other methods of optimization. So it's clear and it's important. Let's consider it. Authors consider a simple quadratic form objective or loss function. Here, theta is a vector of trainable variables, A is a full rank symmetric matrix n times n, and B is a sum vector. So effectively, minimizing the loss function during learning, authors obtain solution of this linear algebraic equation. So theta with a star is a solution of this equation, and on the other hand, it's the minimum of this loss function. We can calculate, we can write updating of trainable parameters during usage of gradient descent. So we just here calculate gradient of loss function. And then authors suggest to consider singular value decomposition of this A matrix. So U and V are unitary matrices, and these sigmas is a sample of specifically ordered sample of singular values of A matrix. So sigma sub 1 is the largest singular value, sigma sub n is the smallest one. And there is no zero singular values because the A matrix has a full rank. Okay, what they want to do further, they want to rewrite the vector of trainable parameters in the basis associated with the right singular vectors. And also they perform some shift here. So looking at this change of coordinate, one can note that during learning, x should strive to 0. So if time increase, x decrease to 0. Okay, and it's possible to rewrite the gradient descent method in terms of new transformed trainable variables. So one can obtain this equation and then use this recursively, apply it recursively. And here you can see the final result. So the vector of trainable variable on 0 moment of time related with the vector of trainable variable in t plus 1 moment of time, and convergence of the gradient descent depends on this factor in the parentheses. So if you want the gradient descent converges, this factor should belong to the interval between minus and plus 1. And this condition gives us the condition on the learning rate. So the upper limit of the learning rate should be determined by the largest singular value. But in the same time, the rate of convergence of gradient descent, the rate with which the loss function coming to the minimum theta with a star is determined by the smallest singular value, sigma n. So the main idea of this part of paper is to make this kappa, this condition number of the A matrix, as small as possible.
Katya, I think I'm still missing something. So can you go back? There are two places where the trainable parameter appears in the gradient descent. It appears as you have here. No, in the transformed one, in the one that you transform. Yeah. So it appears here, of course, because you change the variable with which you change, but it also the gradient itself, because you are differentiating the loss function with respect to the variable x, right? So so there are two places in the gradient descent where variable appears. It's x dot equals to the gradient with respect to x. So you have to change x dot on the left-hand side of the gradient descent, but you also have to change the variable with respect to which you are differentiating. And I don't see that here. The gradient itself has to be modified. If you go to new coordinates, then the gradient itself has to be modified.
I verified this formula. If we just use this formula in origin coordinates and just multiply it on V transpose and subtract this term, then we will obtain this formula for.
But hold on, if you go on the formula above, there is this gradient there, and this gradient further to the right, yeah. So no, to the left, gradient.
Gradient.
Yeah. So see, this gradient is with respect to theta.
Yes.
Okay. So that's gradient now going to be with respect to x if you change it variables.
No, real trainable parameters are theta. And we just can rewrite this gradient, so gradients with respect to theta, but in terms of x.
So you're not writing it as a gradient with respect to x. So you're not rewriting it as a gradient descent equation in new coordinates then. You're not doing that.
Let me.
I guess they just studied learning in original coordinates, but using the transformed coordinates.
That's fine, but then that's what I'm saying. There, if you do that, there are two places where you have to change variables. Basically, on the left-hand side of the stochastic gradient descent, you know it better than I, Katya. You know, we've done this transformation, right? So there is one place that you have to change the left-hand side of the stochastic gradient descent equation, and then the one place on the right-hand side of stochastic gradient descent equation, and that's what I see that you've done it for the left-hand side. You've changed the variables, which are changing.
Use this formula.
Yeah, but then there is this nabla basically. Let me see.
No, stop. We can consider this part and this part, and this depicts the gradient descent in terms of theta. Are you agree?
Okay, so you are saying we are in a quadratic limit. In the quadratic limit, this is all there is. And you are saying that in this quadratic limit, I'm just going to change variable theta to variable x.
Yes, we have already performed differentiation here.
Okay, so you already performed differentiation. You have already answer. And it's only in the quadratic limit where this is applied.
Yes.
Okay. Okay. Now I get it. Perfect. Thanks.
Okay. And so the idea is to make kappa as small as possible. Because we want to make convergence better. Okay. And the idea is to multiply A by some matrix P, so-called preconditioner, in such a way that this inequality will be satisfied. Okay, what can we say about this preconditioner? Of course, it should be probably diagonal matrix, because we don't want to have a large increase in computational cost. So P should be probably diagonal. And then what is the idea? It's possible to introduce new loss function, such a form. This loss function has the same minimum as before, so the minimum remains unchanged. But the gradient of the loss function will change in the desirable way with usage of correct matrix P. And this is the idea of this section. But now there is one important note that here it looks like this is some very specific loss function, strange, simple, but if we just perform the Taylor series expansion, any loss function will obtain such a form. So in this case, A matrix here is just a Hessian of the loss function with respect to trainable variables in some point.
But hold on, Hessian is symmetric. A is symmetric.
Yes.
If you multiply A on the left-hand side by P, this isn't going to be symmetric. Or do you want to multiply it on both sides?
I want to perform this transformation.
Yeah, but that's not going to be a symmetric matrix anymore.
Yes, but it's a modification of a loss function, arbitrary loss function, which was previously expanded around some point.
Right, but now you want to find its minima, you're going to vary with respect to theta, and you'll have to symmetrize PA somehow.
P is diagonal matrix, Katya
Doesn't
said.
matter.
Yes, but maybe it's not a problem that this is not symmetric one.
Well, but you wanted it to have the same solution as the other one. So I'm just trying to find a solution. I vary with respect to theta. What I get, PA plus AP divided by 2. Theta equals to B.
We will have the same.
I don't think it will not be the same solution unless you multiply it on both sides.
We will just we just should multiply P on this equation on the both sides.
Okay, if that's the case, then I think...
And then solution will be the same. So
yeah, but that's not the equation. So you can multiply this equation on both sides with P. Okay.
And gradient here should
be. That's no problem.
Yeah.
But when you go to your loss function and you try to find the solution by varying theta, you're not going to get the other one because you have to vary both theta on the left and theta on the right. So it's not going to be like PA theta equals to B. It's not going to be a solution.
Why?
Because you have two thetas to vary on the left or on the right. Basically, there'll be
the minimum will remain the same.
The minimum, so the minimum will be like symmetrization of PA. PA plus AP divided by 2, which is not the same as what you had before. You understand my point, right? So when you differentiate with respect to theta, you have to differentiate both. You know, the second term is okay because there's only one theta. So it's going to be, like you said, it's going to be P times B, right? Basically. Now, but the left term is not okay because here you have to differentiate with respect to one theta and the other theta.
Maybe I didn't catch you. Sorry.
Well, okay, so PA plus PA transpose, if you put it there, let's say instead of PA you put PA plus PA transpose divided by 2. That would be equivalent when you do variation with respect to theta.
So the idea is to preserve the minimum and change gradients. Is it possible?
It's possible, but then you have to put p's on both sides. You have to just so then you're saying I want to change variables. What you're saying is the following: I just want to change variables around the stretch it in one direction, contract it in the other direction. So to do that, you have to multiply theta by p. And so there has to be two p's where have to appear. One p is going to be...
it's possible, I agree, but...
It has to be, that's the only way. You have to have p on both sides.
Okay, maybe.
If you have p on both sides, then yeah, that will be the same.
Okay, so...
Okay, maybe, okay, sorry. I mean, I'm just trying to... When I see something not symmetric, it just has to be symmetrized somehow.
Okay.
In order to be quadratic. Okay, go ahead. Sorry.
But idea here to change this Hessian by multiplication on the left side by p, some specific p. And okay, they just say that there are some methods. There are already some methods which use the direct calculation of Hessian, and then they use its transformation for optimization of gradient descent. So they suggest another way. They just
Adam is like that. Adam works just like that. Yeah.
Adam, yes, by yes.
You basically do exactly that.
You use information about Hessian second derivatives. Yes.
Yeah.
Okay. But they suggest another way. They just say, let's change weight matrices. So let's introduce preconditioning not before Hessian, but before the weight matrices. And effectively, they claim it will give us the same result. And it is a good way because we shouldn't calculate Hessian directly. So we avoid computational complexity, but obtain the same results. So they just suggest such an architecture. So here weights are preconditioned, and only then these preconditioned weights are used for activation. So this is a form of a new preconditioned network. These matrices are multiplied by some p. Okay, and what is p? Authors claim that it's possible to use raw equilibration preconditioner. So it's a diagonal matrix, and each diagonal element of E sub k is determined by the inverse of the 2 norm of ith raw vector of wk. So okay, and according to van der Sloot's theorem, kappa for this raw equilibration preconditioner will be at least not better than other diagonal preconditioners. So we have this inequality, and of course we can use it for preconditioning of wk, every wk. Okay, and the next, I would say, main theorem of this paper claims that if we perform this preconditioning of weights, this leads us for the same inequality, but for Hessians of new neural network. So kappa for modified neural network is better than the kappa for initial neural network. And let me pass through the main steps of this evidence because it's important.
Okay, so equilibrate is the one that is stretched, or the one that
equilibrate is just the same preconditioned.
Okay. Why do they call it equilibrate?
It's just another notation of the same network, as far as I can understand it.
So it's not like a network that you get after the system equilibrates. It's something.
No.
Okay.
Because according to context, it is the same. Okay. Let's consider loss function. So theta are the vector of trainable parameters. So the dimensionality of trainable parameters is equal to p. The dimensionality of output is equal to O. Dimensionality of subspace of output neurons. C is a sum loss function. F is a prediction of neural network. X and Y are input and output vectors. n is just a mini batch size. Okay, and we want to calculate gradient. We can do it. Here, there is expression for the gradient of L with respect to theta. And first of all, it's possible to calculate derivative with respect to f, with respect to predictions which a neural network will give. And then we can calculate f with respect to theta. So we have some Jacobian metrics, including partial derivatives of predictions of network with respect to trainable parameters. So it's an important metrics for further analysis. And then we obtain this gradient and making the same differentiation of composition functions, we can obtain the Hessian. Hessian includes two terms. The first one is a Gauss-Newton term, usually dominant, and the second one is often small, especially near the minimum of the loss function. So I think that there is some additional theorems proving it, but authors are concentrated on the first term in this expression. And then they consider some inequality, which is also correct. So they imply it for the calculation of kappa for Hessian. Here they note that kappa conditional numbers for df and df transpose are equal, and we can rewrite kappa for Hessian in this form. And here I would like to note that when we modify neural network, when we use the preconditioners of weight matrices, these metrics will not change because it includes a derivative of the loss function with respect to outputs, with respect to predictions of the network. So it's just determined by the form of the loss function, for example, mean square or cross entropy. But this multiple, this matrix, can be modified with the weight preconditioning. So let's consider it. I would like to remind you that df is a matrix, Jacobian matrix, including partial derivatives of outputs with respect to trainable parameters. So what is the expression here? It's just the implementation of chain rules, just a backpropagation method. And this expression illustrates just derivatives of neural network predictions with respect to weights coming into K layer. So what is the strange thing here? The summation, it's not the usual algebraic summation. It's just concatenation, horizontal concatenation of blocks of the entire whole matrix df. So as far as I understand it, we are dealing with this structure. And okay, we want to calculate kappa for this. We can calculate kappa for every block. How can we do it? We can calculate this derivative, which illustrates just derivative of the neurons on K layers with respect to neurons on the K-1 layers. So it's a standard backpropagation, by the way. We can take into account that kappa for diagonal matrix of equal element is equal to 1. Then we can simplify the expression for kappa of this block. So it can be modified as follows. Kappa for one block for K block here is just has a upper limit expressed in this form, which can be expressed in this form, according to this formula. Okay. So what is the final statement of this theorem? The authors claim that the kappa of entire matrix DF can be limited by the sum of kappas for every block. Kappas for every block. And this is a strange statement for me. At least it's violated for arbitrary matrix A, for example, consisting of different blocks. So, but if we assume that for some neural networks, for some conditions, this final system is correct, then we can just make kappa of weight matrices smaller. Then we can make smaller the upper limit of kappa of DF matrix. Then we can make the smaller kappa of Hessian matrix. And then we really can make the convergence of gradient descent better because of reasonings in previous section, previous reasonings. Okay. So they claim that they obtained this result, and maybe it's correct, but at least I think more proofs of this statement should be provided. And let me just give you some example. For example, we have a matrix A. It consists of 2 blocks. And we want to find example which violate this inequality. Let's consider such matrices A1, A2, and whole A. I would like to mention that if we consider A as a DF matrix, then what is the first row? It is a partial derivative of the first output with respect to this weight, and this weight. And the second row is just consists of derivatives of the second output with respect to all weights, and there are no biases here. So as far as I can see, the DF matrix can have such a form. And let's calculate kappas for this A. And we can see that for small enough epsilon, we have the opposite sign in the inequality. So maybe there are some problems with the proof of the theorem. But by the way, there are very good results and numerical results. And in the experimental part, authors give examples of weight conditioning applied for different architectures, not feed-forward, for which the theorem is proven. They consider, for example, convolutional neural networks. They also consider transformers and many other architectures, and they have really good results for all.
Well, those architectures are also feed-forward, so just examples of feed-forward. So it should apply to both convolutional and transformers.
Yes, but
if it's correct, if the theorem is correct, or if the maybe the theorem is not correct, but for the particular architectures it still holds, then it would be interesting.
Okay, I agree, but I'm not sure that
it's correct. Yeah, I understood. Yeah, that makes sense.
Okay. So let's consider some fixed architecture. And 3 methods of its optimization, normalization. So the first is a batch normalization. This method is used in all 4 experiments for fixed architecture. So as far as I know, Bayes normalization is the technique which makes every neuron have the 0 mean value and variance is equal to 1 among the mini batch. So it's some normalization of neurons. And on the second and third experiments, they used also weight standardization and weight normalization. So some also well-known technique of normalization of weight matrices. And in the fourth experiment, they used weight conditioning, explained theoretically in the previous sections of paper. And let's consider CNN inception architecture. So you can see that blue line is a better if we consider the train loss. So and accuracy also demonstrate good results for using of weight conditioning because the convergence is really faster. But if we consider, for example, another architecture, it's not also faster, but it's even better. So the accuracy, final accuracy, is better than for other optimizers. So they also provide in paper other results demonstrated in different tables. And so in many architectures, this technique of weight conditioning works good. So
I have a question, but you're talking about architectures. What about the learning algorithm, right? So have they all tried only stochastic gradient descent, or have they tried Adam?
As far as
because I think the Adam should be compared because really that's what the.
I'm not sure, but
okay.
I considered convolution network, and
that's architecture, right?
I mean, stochastic gradient descent with some mini batch equal to 128, something like this. But I'm not sure that everywhere the same algorithm of learning. But at least in part of the experiments, the stochastic gradient descent is used, and also they use this weight conditioning, which made results better and made convergence of algorithm better. So the experimental results are really good, but according to theoretical reasonings, I'm not sure, but maybe I don't understand something in notations and etc. But thank you for your attention. It's my presentation for today.
Thank you, Katya. Very good.
Thank you.
Okay. There are questions, comments.
The paper referred to some supplemental material, like they prove the theorem 2 there apparently, but I can't find it. Do you have access to it? Supplemental material. It's not inside the paper.
Yes. Katya looked at the supplemental material. So
for the I noticed that you had some...
It's from supplemental material. Yes.
No. She actually tried to follow the proof through the supplemental.
I noticed
there's no proof in the actual.
But I was trying to find the proof. Where is the proof here? And I couldn't find it.
She can post. Actually, can you post in the Journal Club Telegram chat? Just so that people see the supplemental material.
Just different file, yes.
Yeah. Okay. Other questions?
Thanks for the talk. So it's basically like within every layer, this transformation is applied to the weight, right? If I'm understanding correctly.
If I understood the question correctly, then they considered implementation of weight conditioning on of every layer in this theory, but in numerical experiment they said that they used weight conditioning only for initial convolution layer and final layer, for example.
Okay.
By the way, this conditioning is also similar to layer normalization. Basically, it adjusts the tensor that propagates the signal by adjusting its weights. So this is also readjusting the weights, but by not looking by looking at the spectra, right? So they actually have to calculate the singular spectra at every layer in order to know how to precondition it, right?
They used just elements of weight matrix of every layer to calculate preconditioner.
Yeah, so if they first calculate singular values and then they use it to calculate
No, as far as I can understand, no.
So what's the formula for the P then? Then maybe I'm not missing. What's the formula for the P?
P is just a raw equilibration. So
right, but how do you calculate it?
They use previous. I think they use the previous form of weight matrix.
Right. So you take a weight matrix WK and use it to calculate P sub K, right?
Yes. Yes.
Okay, but how do you do it? What is P sub K as a function of W sub K?
Each diagonal element of E sub k determined by inverse of the two norm of the ith row vector of WK. So they just calculate norms of rows of WK matrix. Inverse norms. Inverse two norms. And they then use Van der Lewis theorem.
So they just like so they treat like rows like vectors and they renormalize them. Is that the idea? They normalize them.
Yes, they normalize and but it's not just normalization. It's just it also leads to this result, as they say, leads to this result. It's not just some normalization of weights, but also change of Hessian.
No, but that's what happens as a result of the renormalization of weights. But the way they implement it is what you're saying is just renormalizing the weights. That's again very similar to the layer normalization, but maybe with a different form. I have to think about this. Okay, sounds good. Other questions? Well, thanks everyone for coming. Thank you, Katya. It was very interesting.